So let's start our first class. Our first lab is always talk about microscope. So this is a material, same as the textbook, PDF version on eCampus, but I printed out for you. So we're going to talk about the chapter 2. So let's talk about is Lab-1, microscope use. So first of all, we already learned in lecture, what is a microorganism? Microorganism, we are saying it is too tiny or too small to see by naked eye. So we need a tool, the tool called microscope. Now microscopes, there are lots of microscopes. What you have on your bench and right here is a very common one. This is called light microscope. And also it is one category of the light microscope we call bright field. So what this means, light microscope, which means the energy resource is light. Then what means bright field? This is certainly you already know. If you have a glass slides, and we're gonna make the specimen or we make a sample, and then we use a microscope to do the observation, what you will see, the background is light. And then the specimen is showed up, some color or black. So this is called specimen, or we say sample. This is called bright field light microscope. Why we say this? Because we're going to, in contrast to dark field microscope, we will mention in the lecture. We don't have it here, but we will mention in the lecture. So what we have here is light microscope bright field. Okay. So let's introduce you this structure a little bit. So first of all, this guy, when you hold on, I usually turn this way to hold on. This is a big arm. You hold on the arm and it has a right hand hold on the arm, left hand is hold on the bottom. Otherwise it's gonna fall off. You can't do like this in chatting. Oh, it's gonna very easy to fall off. Okay, make sure always two hands. And you come here, put on your bench, then we're gonna talk the structure. So the first question is very simple. What is the most expensive item of a microscope? If you can think about it, is the lens. The lens is the most important item. And there are two types of the lens. One is you use your eye, go ahead to see. That is closely attached to your eye, which is called ocular lens. Another one is down here. You have a very short red line called 4x. Then you have a yellow line which is called 10x. A blue line, 40x, and the white line which is 100x. What is this called? A objective lens. Because it's close to the objectives, which means it's a specimen. So we have objective lens. Okay, we also talk about using microscope to see the observation of microorganism, because microorganism is too small to see, too tiny to see. Therefore, it comes out with our first terminology, total magnification. Okay, how to calculate the total magnification? It's very easy. The magnification of ocular lens multiple the magnification of objective lens. So, give you a very easy example. If the magnification of ocular lens is 10x, this is a fixed number. Ocular lens, the magnification is always 10x. The magnification of objective lens, if it is also 10x, so what is the total magnification? It is 100x. Example 2. If the magnification of the ocular lens is 10x, and the magnification of the ocular lens is 40x, what is the total magnification? 400x. Okay, one more try. Magnification of ocular lens is 10x, and the magnification of the objective lens is 100x. So what's the total? 10 multiplied by 100 is 1000x. Okay, it's very simple calculation. Now let's look at the ocular lens. It's very simple. We just go there. Okay, these are very fragile, sometimes easy to fall off. Okay, be careful. Not much to talk about. We have more to talk about is objective lens. Okay, we have the stage. We have the control up and down. Okay, we call it a coarse focus, fine focus, we can talk about later. But once the stage is set up, when you twist it, you will see the distance between the objective lens to the stage is different. And what you see. This gives you a second concept called working distance. Distance between objective lens to stage. So what it looks like. Okay. Let's say this is stage. Okay. The light is right here. The light is right here. What it looks like. This is actually pretty short. The second one, a little longer, like this. Good. No good. Okay, we have 10x right here. Okay. Okay, the next one. Looks like this. $40x. The last one. Let's see the color, what it looks like. Should be white one. 100x. So what's the working distance? The distance between the objective lens and the stage is called working distance. You see it? The working distance decrease with increasing of objective length magnification. And the light resource is right here, okay? This sometimes gives you trouble. Okay? What's the trouble? The light is going on. Okay, it goes here. This area is glass. This area is air. This area is glass again. So what will happen? This will happen. The same thing will happen. This will happen. This will happen like this, like that, like this. More fuzzy. What's a phenomenon we'll have? In the physics, did you learn physics? Yeah, what we call it? Refraction. So, light refraction happens when the light passing through different media, from the glass to the air and to the glass. Then what happens is, it will become more and more fuzzy. So, for example, you have a sample right here under this 4x. You didn't see it very clearly. Okay, let's say we switch to 10x. You see, oh, a little bit fuzzy. 40x is okay. When we move to 100x, it's completely, you can lose the focus because more light refraction will happen. How we solve the problem? Put one drop of the oil. We're going to put one big drop of the oil right here. This comes with an important terminology called oil immersion. So why? Because the refraction index of glass equals 1.5. The refraction index of oil also equals 1.5. However, the refraction index of air equals 1.0. So once we put the oil there, we remove the air gap. We deliminize or significantly decrease the light refraction factors because the refraction index of oil and glass are the same. So we think it's the same system. So what's the oil immersion? Remove air gap. Or we say eliminate or decrease light refraction. So that's a third terminology. It is very important. Okay? Now what happened? We talk about magnification. We talk about oil immersion. All these things, we want to make sure our light field microscope has a very good resolution power. So what means resolution power? Can differentiate two tiny close attached particles. That's called resolution power. Resolution power expressed as Rp equals lambda divided by 2 multiple Na. It's a formula. It's a physics formula. So we're going to introduce to you simply. What's lambda means? Light wavelength. So what is light wavelength? Light microscope, the energy is light. Is that a button? So when you turn it on, you all the way to the end. When you turn it on, you all the way to the end. The energy control panel. The light is going from the bottom. This type of the light field microscope, the wavelength is set 622 nanometer. Okay, 2 is a fixed number. What is NA? NA is called numerical aperture. There is a number for that. What is the number? If you look at your objective lens very carefully, switch to the 100x, you will see somehow it is saying 100x dash 1.25. This number is numerical aperture. It's a fixed number for 100x lens. So we always say numerical aperture is like size of the engine. So it's like the size of the car engine, where here is the size of the microscope engine. So we can do the math. What does the RP mean? 625 nanometer divided by 2 multiplied by 1.25. Sorry, I think it's 650. Wait a second. Let me need it. Just 650 or 650. Sorry, made a mistake. Haven't teach for a year, forgot. So 650. 650. So 650 nanometer divided by 2 multiplied by 1.25. That equals 650 nanometer divided by 2.5 equals 260 nanometer equal 0.26 micrometer. This number is important. So I have a question for you. What is the average size of a bacteria? Let's say Staphylococcus aureus. What is the average size of a bacteria? Roughly 0.5 micrometer. Now, why we use light field microscope can do the observation to see the morphology of Staphylococcus aureus? The reason is our resolution power 0.26 is less than 0.5 micrometer. We can do the observation. Then I have another question. What is the average size of a virus? Let's say HIV virus. 0.01 micrometer. Because our resolution power 0.26 is much larger than 0.01 micrometer. So we cannot use light field microscope to do the observation of a virus. And you already know we need to rely on electron microscope. Because the electron microscope, their energy resource is magnetic, is different. Is electron. And with passing through the magnetic and also the resolution power is much lower than the light field microscope. We'll talk about that in the lecture. So that's why we cannot use this type of light field microscope to looking for a virus. Okay? So this is very important. Now, what this means? This tells us the resolution power, the value needs to be the smaller, the better resolution capability. Okay, so we want to be less. We want to be lower. Okay, so that's the fourth one. Fifth one, parfocal. So what the parfocal means? We have these lenses. Now, by the way, I want to say this in here. In this classroom, we will never use 4x. So forget about it. We will always start to find the specimen 10x. Then add 1 drop of the oil during oil immersion, switch to 100x. 40x we will use only once. When the class moving to sometimes later October, early November, when we do the observation of pathogenic modes in a very molded bread, we will use it only once. So the whole class will stick to the yellow color, not the color, the yellow line, 10x objective lens, then oil immersion switch to 100x with oil immersion. So this gives you something, another terminology. We assuming this type of the microscope is functional, is good status. Once you use 10x to find the specimen, then you add 1 drop of the oil, switch to 100x. You only need a very tiny adjustment, which means you only need to use fine focus, the thin knob to switch a little bit. You'll finish the job. That is called parfocal, which means once 10x focused, switch to 100x with oil immersion, focus stays. So say it very simple. Once focused, focus stays. Okay. This is a very good characteristics for a light field microscope. Okay, some other things I have not been introduced to you, I would love to introduce to you, then I'm going to show you how to use it. So there's lots of light going through. Sometimes we don't need that amount of the light. So do you have something to control? Is there a twist here? That twisted called iris diagram. So we using iris diagram control amount of the light passing through objective lens. It should be corresponding to the lens you are using. Which means if you are using 10x, this knob should be fixed put at 10. If you are using 100x, it should be put at 100. Otherwise, the light amount is not going to be enough. Okay? Then we have this stage control, back and forth. That's easy. And the fine focus, coarse focus. So basically, that's a microscope. Then can you use it? Some people can do, some people not. Okay, so what we're going to do, I'm going to do an example for you. So, today's work is very straightforward. Everybody will do 2 observations of measured microscope. You will get a Staphylococcus aureus. And you also come back, when you finish it, you will get a budding yeast. This is Saccharomyces cerevisiae, which is using for beer fermentation. We'll talk later. But before that, I'm going to show you how to use the microscope. Okay? So, I want everybody just come into the front. I'll have the camera faced here to me very clearly. And you guys all come into the front. And I'll show you how to use it. Just come in. Just don't block the camera. Just come in. All right, just stand by there. I'll show you how to do it. Okay. You don't have to wear gloves today, but later on you need it. So what we do? First thing, turn it on. That's very important. Some people doesn't turn it on, then say it doesn't work. Of course, you doesn't plug in, no energy. Then what we do? You can practice a little bit to see these are functional. We're gonna put Staphylococcus aureus. Now make sure you're looking for is the center. Okay, that is the specimen where they located. It's already pre-made. So what we do? We put it in the middle. Oh, this is not very good. Of it, and then we adjust it a little bit. Adjust a little bit. So we use 10x. So we need to go down. Okay. So how we do? We make sure our iris diagram is at 10. Use your hands at your coarse focus all the way up to the place you cannot move. It will not crack it. It's designed very well. Okay, now go ahead to do the observation. You want to see it? So use your hands at your thick knob. We call it a coarse focus. Go down a little bit. 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 To somewhere you can see a lots of specimen. Come here to see it. Don't think I'm lying to you. Look at it, that good? You see something, that's called the specimen. Come here to see it. Can you see it? It's okay, but not very clear. It's just a bunch of things, is that right? Come here to see it. 3 representatives from the whole classroom.
Yes.
Is that good?
Yes.
Okay. But you won't see anything. So we need to do the next step. Is called oil immersion. I don't know whether we have enough. Wait a second. We need to get oil. Okay. We want to see the morphology. We need oil immersion. So grab the oil. How we do it? Remember, never use Z4X. Lots of people directly doing this. No, that's 40x. Only once. So, one twisted, second twisted. Like this, then put 1 drop of the oil. A big drop. This has to be big. Okay, at least cover the circle. So you go here. Okay, now you do a little bit adjustment. See, my hand is on fine focus, very tiny. But one more thing is important. The light needs to be enough going through this objective lens. So this is called iris diagram, needs to be at 100. Okay, then you go back to see a little bit. Okay? See, my hands is on fine focus, is that right? Tiny adjustment, that is called parfocal. Because once it's focused, it stays focused. Then go ahead to see what looks like. You will see a very clear morphology of purple color, grape shape, and coxa. You come here to see it. That's very smart. We don't need a glass because its magnification is 10,000. Is that right?
Yes.
You go ahead to see it. That's what you see it.
Mm-hmm.
Okay. Later on, we're gonna make your own Staphylococcus aureus. Okay. See one final representative. That's what it looks like. Okay. Now that's what you're gonna do. Then you switch to use a body east. When you finished, you can just throw this away or go home. What we need to do, make sure you do a nice and cleaning work for all of us. So you need a lens paper. Do you guys have a? They need a. I think you need your. Sorry, I made a mistake earlier. You need your personal log, and have a lens paper. This lens paper to clean the lens. Okay, very important. Clean the lens. You didn't use it, it's okay. Clean the lens right here. After that, very gentle to wipe it off. Okay, very gentle. You need to make sure you return to the front desk box. I bought this 11 years ago, have 50-50 of each. Right now there's only so many left, which means another 10 years only have 2 or 3 left. So make sure you return to the front desk. Because I used every time is in the very first class as a demonstration, as a warm-up practice for using the microscope. I hope everybody going through today and Thursday, you will be very familiar and comfortable to using the microscope, because it's a basic tool for do the microscope or microorganism research or anything, or teaching or demonstration. We will do simple stain on Thursday, gram stain next week Tuesday, endospore stain next week Thursday. Then we have a unknown number 1. We are gonna use microscope. Then later on we have unknown number 2. We are again gonna use microscope. We are gonna do a 1 observation, use Fourier to see the pathogenic modes. We also gonna use microscope. So make sure you are very comfortable. You can ask Rion and Payton to help, but you cannot have your hands on after 5 classes. You'll still say, okay, Rion, come in. That doesn't help too much. You have to work it independently. Okay, that is you go to solve the problem, set up your own self to go in the first and second classes. Okay, so that's all I have.